Okay, so we're going to pick up where we left off. This y equals 2x plus 4 was graphed in red, and we're graphing the inverse y equals x minus 4 over 2. So at the point negative 2, negative 3, 0, negative 2, 2, negative 1, 4, 0, 6, 1, 8, 2, 10, 3. And join those with a line. And continue the line, so let's see, it's like down to, and there we go. Red line, green line. Okay, now we can answer some questions about this, right? So, when you're copying that down. So the question is, notice the line that was already graphed. So we've got that other little red line here. What's its equation? What's the equation of this line? Okay, this guy was y equals 2x plus 4. What's this guy? Y equals x. Just the line y equals x. And so the question are, so that's y equals x. What do you notice about the graph of the relation and the graph of its inverse relative to the line y equals x? What do you notice about red line, green line relative to this line? Sure, okay. But what do you notice looking at this? Symmetrical about, so the green line is a reflection in the line y equals x, right? See how these guys are like right across from each other here? Same deal, this distance, okay? Okay. So equation of that line was y equals x. And what do you notice? They are reflections of one another about the line y equals x. So that's the third type of reflection. For which you are not responsible on quiz 1. One another about the line y equals x. What's the invariant point? Negative 4, negative 4. What's special about where it's located? Where is it located? On the line y equals x. What's special about the line y equals x? It's a line of reflection. So it's on, now we know that. We know invariant points are on the line of reflection, at least for reflecting about the y-axis, reflecting about the x-axis. That also holds for reflecting about the line y equals x. So it is on the line y equals x. Which is the line of reflection. So invariant point will be on the line of reflection. We will not stretch about the line y equals x, right? We will only reflect about it. Is the inverse relation also a function? So green line, yeah. Okay, so yes it is. State the intercepts of y equals 2x plus 4. So what's the x-intercept? Negative 2. What's the y-intercept? 4. Okay, so x-intercept is negative 2, y-intercept is 4. What's the x-intercept of y equals x minus 4 over 2? 4. And what's the y-intercept? How do the x and y-intercepts of the original compare to the x and y-intercepts of the inverse? Of the original is the y-intercept of the inverse and vice versa. So the x-intercept of the original, x-intercept of the original is the y-intercept of the inverse. And the y-intercept of the original is the x-intercept of the inverse. Of the inverse. One page down, 6 to go. So, quadratic. Let's take a look at quadratic. A relation is described by the equation y equals x squared. How do we write the inverse? So, what do we do to get the inverse? You do what with x and y? Switch them. So we're going to write x equals y squared. Okay. So let's start life out easy. We'll just go x equals y squared. Then we'll worry about, all right, now I want to solve, I want to write it as y equals. So what's y equal to? And not just the square root of x. Plus or minus. Okay. So y is equal. So when I square root both sides, it's actually a plus or minus of the square root, right? Because if I square the positive square root, I get that. If I square the negative square root, I get that. Complete table of values and graph the relation of the inverse. Okay, so we're pretty familiar with this, right? 9, 4, 1, 0, 1, 4, 9. And if I reverse the 9, then I note, hey, look, it goes with 3 and negative 3, so let's just say plus or minus 3. Plus or minus 2. Plus or minus 1. Not plus or minus 0. 0 is just a... Okay, now we say, let's graph these. Now, I can't use blue for some reason. Blue doesn't work. Oh, maybe I can't use blue. Apparently I can't use blue unless... There. So, no, it's switching. Oh, see, yeah, now it's blue. Okay, y equals x squared. 0, 0, now it's purple. 1, 1, 2, 4, 3, 9, 1, negative 1, negative 2, 4, negative 3, 9. Nice smooth curve. And now let's graph the inverse. Oh, I should label that, right? Y equals x squared. And let's sketch the inverse. So when x is 9, I have 1, 2, 3, and I have negative 3. X is 4, I have positive 2, I have negative 2. X is 1, I have positive 1, negative 1, and 0, 0. And this is y is equal to plus or minus the root of x. Does that look like a reflection in the line y equals x? Pretty much, yeah. Okay, think if that's a mirror, or think if I drew those, so if you actually picked up your piece of paper, folded it on the line y equals x, held it up to the light, you can only see one line, right? Like one curve, because it's reflected. All right, let's get characteristics. What do you notice about the graph of the relation of the graph of its inverse relative to the line y equals x? Okay, so it's a reflection in the line y equals x. Or about the line. So say they are reflections of each other. About the line. Y equals x. State the invariant points. Kind of test, I might say pointer points, right? Little parentheses around the s. Maybe there's one, maybe there's more, but in this case there are two. What are they? 0, 0, and 1, 1. 0, 1. What is special about where they are located? They are on the line y equals x, right? They are on the line of reflection. They are on the line Is the inverse relation a function? Is this a function? No. No. That value has two y values, right? So, no. The inverse relation is not a function because domain values are paired with more than one range value. For example, the points 9, -3, and 9, 3. Draw the line that passes through 9, -3, and 9, 3. Okay, draw the line. What kind of line is this? It is a vertical line. Vertical. Vertical line. The vertical line test. If a vertical line can be drawn so that it intersects the graph of a relation at two or more points, then the relation is not a function. In other words, if all vertical lines intersect a function and at most one point, then the relation is a function. Right? So your question is simply this: given that graph, can I draw a vertical line somewhere that's going to intersect at 2 points? And if the answer is yes, then not a function. The points 9, -3, and 9, 3 are the inverses of -3, 9, and 3, 9. Draw the line that passes through that. Okay, so that was 3, 9, that was these guys. What kind of line is this? It's a horizontal line. What type of line is that? Horizontal. I don't know why those, you've got a sheet that's all filled in. What are we seeing? Ooh, the horizontal line test. This may come as a surprise. If a horizontal line can be drawn so it intersects the graph of a relation more than once, then the inverse of the relation is not a function. In other words, in order for the inverse of a relation to be a function, all horizontal lines can only intersect the original relation in at most one point. Okay. And it makes sense then that the horizontal line test, when you interchange x and y, becomes the vertical line test. Right? Because the horizontal line test dealt with what are the x values, and the vertical line test deals with what are the y values, and when we do inverse, we interchange. What are the domain and range of y equals x squared? So what's the domain? And the range is from? Okay. So remember, open parentheses does not include, you may not put a closed parenthesis with an infinity or a negative infinity, right? What are the domain and range of y equals plus or minus the root of x? 0. Domain is from 0 to, and the range is, and what did we really just do? Well, if you're interchanging x and y to get the inverse, then you're interchanging the domain and the range, right? Because domain is all the x's. So in the inverse, it becomes all the y's. And in the original, the range is all the y's, and in the inverse, it becomes all the x's. So the question was, if I have a parabola when I do its inverse, that's not a function, right? Ever. Well, unless we put a restriction on it. Okay. So yeah, if you have a parabola and you do its inverse, you get that sideways parabola. In that case, this is not a function. It's a relation, right? X equals y squared is a relation. Y equals plus or minus the root of x is a relation. Anyways, how do the domain and range of the original compare to the domain and range of its inverse? So they are, I don't know, use a lot of words here. The domain of the original is the range of the inverse. And then just do the inverse of that statement. Domain of the original is the range of the inverse. And inverse versa, the range of the original is the domain of the inverse. if the domain of the original function was restricted in such a way so that its inverse was also a function, what would be the restricted domain? So if we're going to take this original and restrict it, how could we restrict it to make the inverse a function?
Could y not equals lower than 0?
Y lower than, well, there's no y's lower than 0 right now.
For the inverse. So
Oh, so in the original, then you want x to be greater than 0.
yeah.
Okay. So if x is greater than 0 on the original, so if we restrict it so we don't have this, then the inverse is simply going to be that part. Yeah, so that would work. So what would be the restricted domain? So the domain would be, say, 0. What did I say never to do? Yeah. So the domain would be 0 to infinity. Is that the only possible one? What else could we do? Yeah, what if we went this way? So how would we say that? What would the low number be then? Negative infinity up to 0. So we could do from negative infinity to 0. Okay, what else could we do? So remember, we're just working on domain here, right? Not working on range. We're saying the original. So I mean, you could say, well, you know, what if this were, I was throwing some kind of an object, and I'm only interested from 1 to 3 seconds or something, right? And say, okay, yeah, it works. Go 1 to 3. If you don't want to be odd, you go from 2 to 4. So basically anything, as long as what? As long as we don't have a horizontal line, right? So as long as whatever we restrict the domain to, it passes the horizontal line test. So I can't say from negative 1 to 2, because then I'll get a horizontal line. That would be no good. Part D, notation. If the original function is described by y equals f of x, then its inverse can be described by x equals f of y. If the inverse of a function is also a function, then its inverse can also be denoted as f inverse of x, right? We're saying it's the inverse of a function, which is a function. This notation can only be used if both the original relation and its inverse are functions. Okay, can we say determine f inverse of x if f of x is 2x plus 3? So can I say find the inverse function? Yes. Okay, why? Yeah. Yes, it's the original. Original and its inverse will both be functions. Original and its inverse are both functions. Right. As long as the original is a non-horizontal line, right? Can we say determine f inverse of x if f of x is equal to x squared? I just did that, right? So no, because the inverse is not a function, right? So no, because the inverse is not a function. Inverse. Can we say determine f inverse of x? Excuse me, if f of x equals x squared for x is greater than or equal to 0? Yes. The reason is with restriction on the domain, the inverse will be a function. Okay. So we say yes, and the domain has been restricted. Restricted such that the inverse is a function. The inverse is a function. Okay. Good to go. Key concepts. In terms of transformations, the inverse of a relation is the graph of the original relation blank over the line blank. So what are we doing? We are reflecting it in the line y equals x. So reflected in the line, over the line, I would say in, but in over. Reflected over the line, y equals x. Invariant points relation, its inverse will always lie on the line, y equals x. Given the equation of relation, to find the equation of the inverse interchange, x and y. The inverse mapping can be described as xy maps onto yx. Interchange the x and the y. It's become fun when we start doing combinations of transforms as a reflection over that line. You're saying, well, now this goes to here. Right? Don't worry about it. You know, don't worry about it. Just do it as it comes, right? There are no special cases, right? X is replaced by x minus 3, it's a horizontal translation, right 3. There's a negative sign in front of it. X is replaced by x minus 3, it's a horizontal translation, right 3. If the original relation passes the horizontal line test, then its inverse will be a, let's just use function. Function. Oh, did we? I'm still going to fill this in. The inverse of y equals f of x is x equals f of y, or y equals f inverse of x, you know, with an asterisk next to it. Right? It's not a function if, you know, as long as star, as long as the inverse is a function, as long as the inverse is a function. Okay. Otherwise, we can't refer to using that function notation, right? Say, hey, it's also a function. If the inverse is not a function, then you can obtain one by blanking the blank of the original relation. Restricting what? The domain. Restricting the domain of the original relation. The domain of a relation becomes the blank of its inverse. The range of an inverse, or sorry, the range of a relation becomes the blank of its inverse. The x-intercepts become the, and the y-intercepts, forget you fill that in, right? So x-intercepts become y-intercepts, y-intercepts become x-intercepts, right? So if you're drawing an inverse, right, it's kind of easy. I got this point, it's an intercept, so now it moves down here. Any points on the line y equals x are invariant points. I can plot those. I can pick a couple other key points and just take the, you know, interchange their x's and y's. Oh, well, so then maybe we can graph. Practice. Complete the following charts. Note the line y equals x has been drawn on each grid as well. Now I don't think we can do all of these. You know, so we'll do a set, a subset. The relation is set of ordered pairs. 1, 2, 2, 2, 3, 2. What's the domain? 1, 2, 3. What's the range? 2. Function or not a function? So I'm going to use like f and nf. So yeah, it's a function, right? Inverse of the relation. For e to k, write the equation for lambda k. So this is not e to k, this is just a. So what's the domain of the, and what's the range? Function or not a function? F or nf? Not. Why not? Well, because the points are 2, 1, 2, 2, 2, 3, and you have an element of the domain with repeated range elements. Graph the inverse on the, oh, so first we need the domain. Domain? X belongs to the reals. Range? Y also belongs to the reals. Graph the inverse on the grid shown. What do we do to graph the inverse? How many points do I need to graph the inverse? Need at least how many points? I only need 2. It's a straight line, right? I'm going to go for more than 2. I'll make sure. So, okay, I've got this one, right? That's invariant. This is 0, negative 1, which becomes negative 1, 0. This is 1, 2, so that becomes 2, 1. So any other? This is negative 1, negative 4, which becomes negative 4, negative 1. And if I had a ruler, those 4 points should line up, right? Now, if you draw this using only 2 points, you're always going to get a straight line out of it, but it might not be the right straight line, right? If you do 3 points, at least then you've got a little confirmation. Oh, look, they're all on the same line. And 4 points, yeah, okay, it's probably pretty much it. What's the domain of this? Oh, is the original a function? Is the, whatever we call that thing, inverse a function? So they're both functions. I don't know. How many of these should we do? How much time do we could do a bunch. Okay, you want to do this together, or you just want to give this a shot? And then give it a shot? Okay, give it a shot. Okay, so blah, 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 right? 2 to infinity, and range is negative infinity to infinity. It's not a function. The original, the black line. Graph the inverse, we just interchange domain and range. Ending up with a parabola, and that is a function, so that's... I meant done D, I didn't mean done. I did restart the recording. So you can draw it first and then work out domains and ranges. You could do the domain. Once I do the domain and range, I'm just going to rewrite them as the range and domain of the inverse, right? And then just make sure everything kind of matches up with the way you think it should be. So a horizontal line becomes a vertical line, or a vertical line becomes a horizontal line. If I fold this along that, so you can always pick up your paper, kind of just hold it up to the light and say, yeah, okay, it's lying on top, right? Like this is going to move to there, and these guys are going to go over to there. I don't know. How many of these should we? Well, let's do E, and then you do F. How's that? Okay, A, B, C, D, E. So there's no, what is this? Describe it in words. X squared minus what? It's a parabola shifted down 1 unit, right? Okay, so it's just a basic parabola. It hasn't been stretched or anything like that. So it just looks like this. That's negative 1. What's the domain of every parabola? Okay, what's this range? Which now allows me to go over here and do this. Nothing allows me to do that. Is the original a function? Yeah. Is the inverse a function? No. And what did it say? It said like for e to k or something, we're supposed to do the, write the inverse as y equals. Okay, so the inverse, I want to do the inverse. So I'm going to write x is equal to y squared minus 1. Y squared is equal to x plus 1. And y is equal to plus or minus the square root of x plus 1. Okay, that's the inverse, which is not a function. Right. So square root x is that sideways parabola, but then it's shifted which way? No. X is replaced by x plus 1. It's shifted left, right? Right. So here I want to draw a sideways parabola, but I need to kick it left 1. That's got to be negative, right? What's that? 0, negative 1. What's that? Negative 1, 0. Right? It's got to be. That's inverse stuff, right? If x is replaced by x plus 1, what's that in any language? Horizontal translation, the last one. Okay. Now, we have a restriction. Okay, so your turn. Do the restricted one. F. Do F. I'm just going to back up here and go through a couple of these. I don't know where I paused, so anyways, here's some answers. And if you need an explanation, wise time is great for that. And here's some more answers. Except for G. And there's H. So, yeah, we did H, you can do I, so then let's do J. What kind of function is J? It's a rational. Okay, so 1 over x. Do you know what 1 over x looks like? Okay, but then it's been translated what? 1 to the left. Okay, so rational would look like this, right? But now it's translated 1 to the left, right? Because we'd say here, what can't x be? Right? It can't be negative 1. You're not allowed to put that in there, right? So here's my negative 1. And then here's what the new. So that's what this graph looks like, right? Now, how do we say a domain that says you can't be negative 1? Here's how we say it. We say you can start at negative infinity and go up to negative 1, but you're not going to include the negative 1, right? So parenthesis. And together, you're going to put that with all the numbers from negative 1 to infinity, but you can't include the negative 1. Right? So that's how we exclude negative 1. You've got open parentheses on both ends with the negative 1, saying does not include negative 1. From negative infinity up to, but not including negative 1. And from not including negative 1 up to infinity, right? So the slightest amount below negative 1 to the slightest amount above, but not including. That's how we exclude negative 1. And the range, what doesn't the range include? Does not include 0, so we do the same deal with the 0. Right? We use round brackets to say, no, you can't have a value of 0. Right? You can't have a value of negative 1. Another notation, you could say a set of all x such that x is not equal to negative 1. X belongs to the rails. That would also work. Okay, so if we go here, I mean, once I filled in my domain and range, then I can fill this in. And then I can fill this. And so now I've got to interchange my x and y, do a little bit of magic, aka algebra. And we don't necessarily want to stop there. Actually, there's a couple ways we can do this. So this is just x over x. So it'd just be y equals 1 minus x over x. That's one way. Or we can do this. And then say xy is equal to 1 minus x. And then say y is equal to 1 minus x over x. So in this case, we go directly to this form, and in this case, we had to change this to x over x and go 1 minus x all over x. Okay. Either way, the same one, same answer, right? This might be a little bit easier, right? So expanding the brackets first, then moving stuff and dividing. Is the original a function? Yes. Is the inverse a function? Oh, there's restriction. What's restriction? So x cannot equal 0. That makes sense, right? Because here, x can't equal -1, that's the domain, which means we won't be able to get a -1 out of here, right? I can't make this equal to -1. Okay? And the domain of this is that x can't be 0, which was the restriction on the range. So this is also a function. Okay, so it's k. Okay. So here's a mildly botched version of y equals 1 over x, right? Because it shouldn't cross that. So it's got an asymptote there and an asymptote there, right? Now, what transformations would I do to end up with 3x over x minus 2? What's the first transformation? How is that even 3x over x minus 2? So we're going to have to do a vertical stretch. Well, actually, it's not 1 over x, is it? It's like x over x. I don't even know what it is. Never mind. Forget it. To do the horizontal, just throw in a large value for x and say, what am I getting to? So it's like 3,000 over 998. That's getting close to 3. It's like 30,000 over 9,998. It's getting closer to 3. It's like 3 million over 2 less than 3 million. Or sorry, 2 less than a million. That's still getting really close to 3. So it's 3. Okay, so what do we do? So if I want to write the inverse of this, what am I doing? Okay, everywhere I see x, I'm going to write. And everywhere I see, I'm going to write. Okay, so this becomes x is 3y over y minus 2. Okay, so we're just going to cross multiply that, get x times y minus 2 is equal to 3y. We're going to expand this to get xy minus 2x is equal to 3y. We're going to get all of our y's on one side, so I'm going to write xy minus 3y is equal to positive 2x. So I'm moving y's over to the left and x's over to the right. I'm going to factor out the y, and then I'm going to divide. Okay, now you know, x can't be 3. X can't be 3. I will not get a value of 2, right? Because put in a large, you get 2 million over, like, 2 million over 999,997, which is almost 2. Okay. So that's that one.
Would you, like, on our test, would you just show our work? Could we just, like,
Well, I want to see this work.
well, can we just switch the 2 and the 3? That's like,
Just because it works like that here? No. Oh, of course you may, but don't expect full mark. Just, you know. Maybe that works in general for that. I don't know. I'd have to look at it a little carefully, but yeah, it might work actually. But you can't just do it. For me, it's more. The point 48 lies on the graph of y equals f of x. What does this correspond on y equals f of y? So 48, and I say x equals f of y. You say that it is 8, 4. You're interchanging x and y. So you look at this, and you say, oh, somebody did a reflection in the line y equals x, which is the inverse, which means I interchange x and y. What is the image point AB on the graph x equals f of y? BA. Will the inverse of a linear relation always be a function? No. When would it not be? So,
either vertical or horizontal.
okay, so if the original function is what? If the original linear relation is a horizontal line, then the inverse will be a vertical line, which will not be a function. So no. No. Now it does say explain, right? So you can't just say no. Explain. If the original linear relation is a horizontal line, then its inverse will be a vertical line. Inverse will be okay, which is not a function. Okay, so just say which is not a function. Say which. When a relation along with its inverse are graphed, there is one invariant point at x equals -4. State the coordinates of this invariant point. So, what are the coordinates of this invariant point? -4, -4, right? So, if a relation and its inverse are graphed, then you are reflecting on the line y equals x. The invariant points are on the line y equals x. If x is -4, then y is equal to x, which is -4. So it would be -4, -4. Algebraically, determine the exact value of the coordinates of the invariant points when y equals 2x squared plus 6x minus 3 is reflected in the line y equals x. Okay, we'll just say, I don't know, since the invariant point is on the line, y equals x. Okay, common type of question that you may see, how we're going to tackle this, determine the exact coordinates of the invariant point. So we're starting with y equals 2x squared plus 6x minus 3, but we're reflecting on the line y equals x. So what do we know about y? What's it equal to? It's equal to x. So if y is equal to x, let's write x is equal to 2x squared plus 6x minus 3. Right? We know the y coordinate. Whatever the x coordinate is, the y coordinate must be the same. So we replace y with x. You could equally replace x with y, but it's not really going to make any difference, right? You just be solving for y, and since y is equal to x, once you got y, you got x, etc. Okay, so what do we get? 2x squared plus 5x minus 3 is equal to 0. Okay, so does that factor? Ooh, I think it might. Took the x away. Okay. So what you do when we say, hey, it's on the line, you're going to say, oh, it means y equals x, so where I see y, I'm going to write x. Let's make it a quadratic. So we'll subtract x from both sides. Set it equal to 0. Hope that it factors. So 2xx gives me 2x squared. I want a 5, so let's go plus 6 minus 1, 0. 2x squared plus 6 minus 1. Yep. Okay, that works. Okay, leading us to x is equal to 1/2, or x is equal to -3. And then ultimately answering the question, right? Or what did the question say? What's x? And determine the exact value of the coordinates of the invariant points. Okay, so the invariant points are, what are the invariant points? 1/2, 1/2, and -3, -3. Okay, watch for context. Maybe that's a domain, right? Pretty restricted domain, but it's halves and it doesn't include a half. Doesn't mean that you couldn't write a domain like that, right? So not it goes from a half to a half and doesn't include it. So that's not a domain. If the domain range of y equals g of x R, the domain goes blah blah, and then state the domain range for the inverse. Okay, what's the domain of the inverse? X such that. Yeah, go ahead. C. And the range? Okay, so you're just interchanging the values, right? So if that was from, -5 to 7 and whatever to whatever, you're just interchanging. So you interchange your domain and range. Domain is always x's. Don't interchange it in the sense, right, domain and then throw y's in there. Okay, that doesn't fit. In parentheses, in interval notation, that would work because we aren't saying it's a set of x's or the set of y's. We're just saying it's these numbers. Okay, what's next? We're almost done. For y equals x squared minus 2x minus 6, write the equation of the inverse. Okay, what's the equation of the inverse? Oops. Too soon with the 2. Okay, if I want to do an inverse, let's keep life easy. It just says interchange x and y. X is equal to. Why is it difficult to express the equation of the inverse in the form y equals? Yeah, you got a y squared term and you got a y term, right? So it's not just an easy click over. Okay, so it's difficult to isolate for y. So it is difficult, but not impossible, right? It's difficult to isolate the y, but you could if you completed the square. Right, because if you could write that as like y minus 1 quantity squared plus whatever, 10, then you move the 10 over and you square root both sides and you do the one thing and you can isolate the y. So you can isolate the y, you can't really see it right, like not easily, right? You have to complete the square on this and then do some further work, okay, which we're not asking you to do. Express y equals x squared minus 2x minus 6 in a form so that it is easy to write the, well, if we complete the square on the x, right, y equals x squared minus 2x minus 6, if we write that in completed square form, then it should be easy, right? Because then we only have one y and one x in the expression, right? So completed square form, you're going to do what? You're going to go x squared minus 2x, throw down some brackets, minus 6. And you're going to say that's x minus 1 quantity squared. I don't care how you complete the square. This is how I complete the square, right? Just the fact that you can complete the square is all that's up. So I need a plus 1 there, and then a minus 1 there, and then minus 7. So that's the completed square form. Y equals x minus 1 quantity squared minus 7. To do the inverse, we're going to write x is equal to y minus 1 squared minus 7, or x plus 7 is equal to y minus 1 squared, or y minus 1 is equal to plus or minus the root of x plus 7, and y equals plus or minus the root of x plus 7 plus 1. And that's y equals form for that. Oh, and then the answer to D is already done. That goes down there. Okay, I jumped ahead. Wow, and we're like 10 minutes early. Okay, so priorities, right? What your priority is to finish off the booklet up to inverses, so filling in any blanks that are not in inverses, doing any of the homework question up to inverses, and you've got tonight, all day tomorrow, and tomorrow night to get ready for that, right? To get yourself ready for the test on Wednesday. Okay, so tomorrow we will be starting. There's no review classes in this class, right? So like, oh, let's take a day to review. That's so 20-1 or 10C. It's like, hey, you know when the quiz is, and you got to be on top of it. So, no Henrys tonight, but there is Henrys tomorrow. There is Henrys at lunch tomorrow. I'm around in the morning as well. I'm here at Wise Time. I'm around after school today too, but